Howdy everyone, we're at EdoMech and we're going to be presenting over the Inchworm project today for interchangeable wireless origami robotic modules. Before we get into any details, we're going to discuss our presentation outline. First, we'll give you some background on the project, including who's involved and why it's important. Then we'll discuss the conceptual design, including functional requirements, performance specifications. The technical details of the project are broken up into mechanical, electrical, and software sections. We'll give a bit of an overview of each of those before we go into some of the details of the subsystems. And then after that, we'll show some testing and demos before we get into some of the project status information.
This is the EdoMech team. We're led by our project manager, Joel Casila. Our software engineer is Jonathan Cornell. Our hardware engineer is Joaquin Kierza. And I am James Trapp, the systems integration engineer.
Dr. Lee is our customer, advisor, and sponsor. Our capstone project is based on her previous research into 3D printed semi-rigid origami structures. In this image here, you can see her origami twisted tower designs and the different motion profiles that they can obtain depending on what sort of forces are applied to them.
For our problem statement, existing robotics currently employed for space have a bit of an issue with them being rigid, manufacturing difficult, as well as fuel costs with their associated weight, and has caused a need for a new kind of technology for robotics so that it can lightweight, compact, and lower costs for transport when used in space. Our solution for this issue is to further research into origami-based robotics arms that are much lighter, cheaper, and more customizable for use in space. Continuing with our solution, we are going to be modifying Dr. Lee's robot design with the origami twisted tower for increasing its versatility and mobility while also making it modular so that it can be further developed down the line for research. And we will be documenting our endeavors down further. Additionally, we will be creating 2 functional modular arms that we'll be using for this project.
Each robotic module will have a universal connection on each end. This will allow us to put them together in whatever orientation we want, as well as connect multiple to create different physical setups. We will be accomplishing the motions through tension-based cables. This will be powered by a servo with a pulley. That pulley will have the cable attached to it, which will then be routed through the origami structure, allowing for the different collapsing motions of the robotic arm. Each of the modules will be able to communicate wirelessly between each other. Currently we're doing this over RF with XP modules, and collectively they'll behave as a single robot when they're connected and they're all being powered to do certain commands. So here's our conceptual block diagram for it. As you can see in the center, we have the PCB. We have power going to it, which is then dispersed to all of the different components. We have the servo, the microcontroller, and then the RF communication. And then, as I just stated before, the servo will be connecting and actuating the origami structure, whereas the RF communicating out to a master controller. This is what we call the CAS housing, which is the communication and actuation subsystem. So its functional requirements are to use servos to actuate the twisted tower section, to communicate wirelessly with other modules, to provide intelligence required for wireless communication and motion control of each module, to use rechargeable batteries in order to power the electronics in each module, and to fit within the compact space of the CAS housing, which is pictured here on the side. So for the docking ports, its functional requirements are that it's easily joined with any twisted tower section and with compatible dimensions, that it's capable of going through many iterations of testing in a research environment. Basically, that means that we're able to snap them together and take them apart multiple times, and that we're able to integrate with the CAS housing, which is kind of what's shown here on the pictures to the side, it being screwed on there. So just a brief overview for the performance specifications. We'll get more into all of the specifications for each subsystem as we go over them, but the overview is that the cast must fit inside a space that's roughly 55 millimeters thick, that it's able to communicate and transmit data using serial communications protocols, that the rechargeable battery pack can power the 11.1 volts and 3.3 volt devices that we're using, that's the servos as well as the microcontrollers, and then it's able to maintain communications at less than 6 meters. So here's this is the mechanical FPD that we have for the device. Basically, it's just showing what we mean when we say that the servos are actuating the tower. So they're going to be placed in the CAS housing, which is attached to the in connectors there at the bottom. You can see they have cables in them that are routed kind of like where this yellow line is, that helps pull down the twisted tower.
This is our system level functional block diagram for the whole project. The whole system will be powered with three 3.7 volt battery cells, which adds up to a total of 11.1 volts when put in series. The 11.1 volts will power the servo motors, which will be daisy chained, and it will also power the electronics on board each separate module. There will be a switching regulator on board the PCB, which will regulate the voltage down to 7 volts so that the Arduino Nano can then redistribute this power in 3.3 volt rails to the peripherals in each module. This is the power distribution functional block diagram. It is the power distribution in more detail. This is the servo actuation functional block diagram. As you can see, we have the power going to the servo motors, and then we have the Arduino Nano in charge of control of the servo motors. We'll be using UART communication for these servo motors. The Arduino Nano outputs a full duplex UART signal, but the motors take half duplex UART signals. That is why we have included the THVD 1452, which will translate this full duplex UART into half duplex UART. This is the IMU functional block diagram. Here we have more detail on how the Arduino Nano will communicate with the IMU on board the PCB. For this, we will be using I2C communication. And finally, the XV communication functional block diagram. This is just more detail on how the Arduino Nano will be communicating with the XV transceivers. For this, we will be using SPI communication, and we have a 5 volt to 3.3 volt logic step down converter.
So this is an overview of our mechanical specifications. So this here is broken down into two parts, the housing and then the actual connectors. So for the housing, it needs to be able to secure the electromechanical components that we're using. It needs to be able to contain anything within a space that's roughly 55 millimeters tall or less. It needs to be able to control the physical movement of each arm section. The connectors, they need to be able to withstand about 50 disconnections without fracturing the material or deformation beyond 3 meters, because that's when it starts to actually not work. It needs to be able to support about 1 kilogram of mass, just like on its own without causing any problems. It needs to be able to securely connect all the modules together. So this here is the mechanical design for the CAS housing. The first one that we had printed was printed out of ABS. We plan to use ABS. We haven't had any issues yet, but we're exploring other avenues just in case things go awry. It is assembled with M3 screws and heated inserts. That's where all of these little screw hole points there you can see at the top are, or in the drawing view that we see to the side here. Those are all the circles that you can see on the top view. It has vents, as you can see here, the kind of extrude cuts that are made there on the top. Those are around the servos, and they're used to increase the airflow around them to prevent overheating, especially since they're all in there and all the electronics are butted up next to each other. And it uses pulleys, which are there on the side. You can see on the top view there that there's a little hole that the cable is able to come out of, and that's used to actuate the origami structure. And then Moving on to the mechanical connectors, that's also printed out of ABS. It has offset diameters, so if you see in the top view there that the outer diameter has it's not consistent all the way through, that is because, again, this is a universal connector. Each piece will have the exact same connector set so that you can have the male and female components on both. And then we have a swept profile on the actual tab. So what we're using for the universal connector is basically a snap feature. You can see a cross-sectional view of it in this top left picture, where we show just the dimensions of all of the major aspects of it. All the measurements aren't quite as important, but what is important is that we have that profile swept along the outer diameter of it. So if you see in the 3/4 view, the tab actually juts out and stays along that edge. That is to add additional strength to the tab to it. That way it can withstand more connections and disconnections.
These are the electrical specifications that were made by our sponsor and advisor, Dr. Ki Julie. She asked that all electronic components must be fit inside a space that is roughly 55 millimeters thick. The modules must have the ability to stay powered for an extended time for at least 1 hour of continuous testing. It must be powered by a rechargeable battery pack, and these rechargeable battery packs must be able to power the motors, which take 11.1 volts, as well as all the 3.3 volt devices. The PCB must be in charge of distributing the power to the different voltages. We have decided that there will be 3.7 volts and 1 amp hour LiPo rechargeable batteries. This will give us a total of 11.1 volts, and it will be divided into it will be regulated to 7 volts so that it can power the microcontroller on board the PCB, which will be in charge of distributing power using 3.3 volts to the different peripherals that we'll be using for the project. 2 AX12A Dynamixel servo motors with digital control will be interfaced to the Arduino, which uses the RS485 translator. We will have one XB Micro 3, which is a surface mount model, which has an integrated antenna. We will use this for the wireless communications. And we will have one ICM 20948, which is a 9-axis IMU. We will use this to track position data in each of the modules, and we will also have all required accompanying circuitry. This is, for example, the logic level step downs. This is the alpha schematic, which was developed in Altium. At the top, we have the switching regulator. On the right side, we have the IMU at the top right corner. Down in the center, we have the Arduino Nano. We have the translator to communicate with the motors. We have the XB on the left side. And down at the bottom, we have the required circuitry for the logic step down. This is the alpha PCB design. This board is around 3 inches by 3.5 inches, so it will fit snugly in our designed housing. This is just a 3D version of that board. For the PCB, we have included test points. These test points are included to conduct easier performance reviews on the alpha PCB. The test points are placed strategically in the following location: voltage input and output on the switching regulator. The Arduino Nano voltage input, the 5 volt output, and the 3.3 volt output pins have test points on them. All JTAG headed pins for all the I/O devices have also test points on them.
For our software specifications, we will be using serial communication protocols with each one of the modules, and must provide effective controls for the tower movements and be able to wirelessly communicate with the other modules. Each module within the system will need to be able to recognize its position within it and act as a single unit along with the other modules. In addition to that, we'll also need to provide information about the module's actuations, and position control must be efficient within a 2.5 centimeter range. and the communication must be maintained at a distance of less than 6 meters. For our software interview, we have created this flowchart seen here on the right, where all of the code we will be using will be for the Arduino. It will first establish a wireless connections using the XBRF modules to communicate with other modules who also have XBs. And once it has initialized its sensors, it will do a repeated loop where it will perform movements, take a snapshot, so to speak, of the IMU data at that time, send it to the other modules, more specifically to a module that is connected to a computer so that it can check to see if the data was received and then serial printed for real-time analysis as well as for analysis later on, since the serial printing can be later recorded. For our actuation control software, we will be using UART communication protocols where the servos can operate at either half duplex or full duplex with the help of the translators for more precise control options. Rotational position values can be defined by the software so that we may have precise control of the exact movements of the servos. And the main loop that we have going for the actuations is that it will check to see what is the status of the towers currently, so that if the towers were at an expanded state, the servos would then check to see and then tell the servos to collapse it, and vice versa for when the tower is collapsed to later expand it, the servos, depending on its current state. Here we have the software flowchart for the actuators, where after upon initializing all the necessary connections and sort of libraries and variables, we have the main loop that checks to see if the tower is either expanded or contracted, and we'll toggle the state of the tower with the other two functions, with expanding the tower and contracting the tower, where it will simply check to see where the servos are currently and make necessary movements as needed and stop them once completed. Next, we have with the IMU software, we will be using I2C communication protocols to read the data as an unsigned 8-bit integer for the gyroscope, accelerometer, and magnetometer sensors. The data will then be scaled for easier interpretation since the raw data values given by the IMU isn't usable, and then will be transmitted to the other modules via the XBs. In addition, the IMU data will be transmitted to an external computer so that it may be seen for real-time data analysis or for later analysis once complete. Here we have the first stage of the IMU software flowchart, where we have the main loop where it regularly checks if the IMU data is ready, and it will simply just repeat itself until it becomes ready. Once it does, it will get the data, scale it, and then send it to the XB. And the functions following that are all the necessary functions to scale the data as needed, as well as gathering data from, you can see here, steps, padding value as needed, requiring the raw data. Here we have a continuation of the IMU software flowcharts, where it will check to see floats, values, and scaling as needed, as well as reading the necessary IMU values. Next, we have the wireless communication software. The software will primarily be done with the Arduino Nano and will read the IMU data gathered by the IMU sensors and will send it as necessary to the external computer, where an XB module will be waiting to receive data. There are two primary functions with the XBs, where one will simply just take the IMU data and send it as needed. The other will perform an action based off a packet derived from the data, depending on which module the software is being attached to. For case 0, it will only send whenever when it hasn't received data from the coordinator. And it should be noted that only the coordinator can send the IMU data to the external computer, since the other units will be routers and will be only capable of talking to the coordinator. And as you can see here with case one, what Nader will tell the other modules to move and give the respective INU data as needed. And for case 2 and 3 will be for the routers that will send the data to the coordinator so they can send it to the external computer. Here we have the flow chart for the XP wireless communications, where after initializing the necessary variables and XPs, it will then either go between transmitting the INU data after the INU sensor has gathered it, and the transmit INU data function will package as necessary to send to the other modules. And then the receive incoming package, which, as I explained before in the previous slide, will just do a certain action based off which module the function is being attached to.
Here we have a mechanical demo of our 3D printed housing. Here we're showing kind of how it's put together, as well as you can kind of see roughly the size that we're working with.
Here you can see in the software and electrical demo, you can see the coordinator XP module being connected to the IMU sensor, which in the next XP module you will see is the receiver, where you can see in the monitor is the IMU data being sent. Now, this is just being tested for the time being and will be later improved. And following that will be the code from transmitting XP or the coordinator that will read the IMU data from the IMU sensor and send as needed.
All right. This is our demonstration video for the XP communication modules. On the left here is connected COM7 is the end device of the XP network. And over here in COM6 is the coordinator, which sets up the network for both the XPs. I have already uploaded the code, this being the transmit code for the end device. And as you can see here, may not be able to read it, but this is a packet that it is continuously sending to the coordinator. And when we switch over to the coordinator's serial monitor, you will see that it is continuously getting the packet data at these intervals. And just to kind of show, this is the code for the coordinator.
So this is our schedule overview. This is a generalized Gantt chart that shows the major work packages that our project is broken into. Originally, we started off with some materials research and prototyping, as well as acquiring all the different components for our project in terms of electronics, and then fabricating the different 3D printed mechanical elements. After that, we have software and then testing of the alpha design, including hardware and software, acquiring the twisted tower design, making modifications to it and printing that, and then our beta design. Finally, is going to be our integrated systems testing for the final prototype, and then completing the documentation. So this Gantt chart shows our current progress in the project. All of our preliminary research is completed, obviously. We finished some of our paper prototypes as well. The acquisition for the majority of our electronics has been complete, although there are a few more items that we still need. The 3D printed communication and actuation system housing has also been fully designed, and we've acquired a prototype of that. So for software, we also have completed the prototyping for each of our major hardware components, and we've started to compile that into an alpha code, which is also nearly done. The alpha board is the next step as far as getting that delivered. We did have some delays with that, but we're hoping to overcome that shortly. So for our major tasks remaining, we've got mechanical assembling and tests, alpha board testing, beta code, beta board design, beta board testing, and the integrated system testing. We had some of our 3D prints come out not as well as we had hoped originally, and so we had to reprint a couple times, so we did have some delays with that. We also had some alpha board delays with regarding some of our components on there were too small for the manufacturer that we were originally looking at, so we've had to make some adjustments for that. And then again, beta code is going to be dependent on us testing the alpha software on the alpha board, but we do hope to be back on schedule by testing our alpha board after we've made the necessary adjustments to our other work. And then after that, we'll be working on the integrated systems testing. As long as we can work hard these next couple of weeks, we should be back on track with that, and we might actually be able to get that done a little bit sooner. So this is a more detailed look at our remaining tasks. Basically, we still need to get the alpha board delivered. As I mentioned earlier, we had some delays with that. The alpha code is almost done, but it does need to be refined slightly. The twisted tower, we actually have the CAD for that. However, it still needs to be printed. That requires a very specific 3D printer on campus. That's difficult to get a time slot to print, so we're working on that. The beta board is going to come after we get the alpha board and are able to test the alpha code on it, and that way we can determine what kind of flaws it has and if we need to make any adjustments. So we'll be working on the beta code and updating our PCB design for the beta board as we test the alpha board and alpha code. And then after that, we'll be testing our final hardware once we get everything finalized and finishing up the documentation for our project. So for our labor status, the team had midterms this past week, so we only predicted 75 hours. However, we did manage to overshoot that by about 20 hours. Next week, we're going back to our prediction of 100 hours. And so far, we've worked just under 500 hours for this project. So out of the just over 1,100 hours that we had predicted, we've got 656 estimated hours remaining, spread across the 7 weeks, which means we need to work at least 94 hours a week to meet that goal. Our financial status, we have run a bit over our original SDP estimates. One of the biggest things there was the mechanical elements. The 3D printing of the twisted towers is far more expensive than we had originally thought. So when we get that printed, that is going to run up the budget a little bit. We also went over our budget on parts. We had originally estimated about $530, but we're currently sitting at $600. And out of that, we spent just a little bit over the $534 that we predicted. We haven't spent too much money on any kind of supplies or anything. We spent about half of our estimated budget on PCBs. And overall, our current estimate for this project is about $1,000, which is $332 over the original estimate. However, we're still over $2,400 under budget for the entire project. So in conclusion, we identified a need for basically an improved design over traditional robotic arms. These robotic arms are large, heavy. The rigid body of, or the rigid nature makes them hard to store, and the assembly is a bit more difficult. So essentially what our team is trying to do is create lightweight, cheap, and space-efficient alternatives to those while using origami-based structures. We also want to make a design that's a lot more modular. That way it can be integrated sort of into a great number of different systems, as well as continuing other research. And then the idea of the modularity is that each of the modules can be incorporated into various positions or roles and fulfill different functionalities. So As long as we keep working diligently, we do anticipate to finish this project on schedule.